Okay, great, Anne. So we are going to start looking at magnetism. I've decided to do it like this because the section is basically just theory with a few little application type questions, but there's no calculation. So I'm just going to sort of screen record my phone. Hopefully it works all right. So this is the note that I will send you on WhatsApp, and you'll also find it on OneDrive. So with magnetism, firstly, magnetic force is a non-contact force experienced by magnetic objects within a magnetic field. So there's quite a few words there that might confuse you a little bit. So firstly, non-contact force, it's in italics underneath that, the definition there. It is a force that acts on an object without coming into physical contact with it. And then we've got magnetic objects and magnetic field as well that you might need explanations for. So magnetic objects, I'll talk about that in a little bit, and then magnetic field we'll talk about as well underneath, and I'll show you a little video of how magnetic fields look in real life as well. Okay, so firstly, why do magnets exist? It's because electrons are moving constantly. We know that. They orbit the nucleus, and moving electrons themselves actually have an associated magnetic field due to their movement. Okay, so we looked at electromagnetism with waves. Okay, so we know that moving electric charge results in a magnetic field, which also results in an electric field, but we're focusing just on the magnetic field here. And underneath that, then I've got an explanation here for non-magnetic materials, ferromagnetic, and permanently magnetic materials. So those are the three types of materials we've got in terms of magnetism. You've got things that are non-magnetic, things that are ferromagnets, and then you've got permanent magnets as well. So we're going to talk about the three of these, as well as domain theory and how the domains affect whether a material is magnetic or isn't. So starting with non-magnetic materials, so that's this here. We've got most materials. So talking about magnetic fields. Okay, so the moving electrons have magnetic fields associated with them, right? Now everything's obviously made up of atoms, so everything consists of electrons, and those electrons are moving, and each one of the electrons has its own magnetic field. Now, in non-magnetic materials, the fields point all over the place, okay? So they're all going in different directions, and that means that they sort of cancel each other out. We get a net zero magnetic field. Net just means total. So the overall magnetic field will be zero because all of your magnetic fields, individual magnetic fields, are pointing in different directions, so they cancel each other out. And when that happens, you end up with a non-magnetic substance. So for example, the little diagram below, we've got a plastic ball showing all the different magnetic fields of all the electrons in the plastic ball. Now obviously this is a simplification of what's going on in real life. In real life we've got billions of electrons. Here we're only showing a couple. But in that plastic ball, you can see the directions of the electrons' magnetic fields are pointing all over the place, and as a result, they cancel each other out, which is why our plastic ball is non-magnetic. Okay. Then you get ferromagnetic materials. Now, in ferromagnetic materials, we have these things called domains, and in each domain, so you can see in the diagram here, the domains are shown with sort of the little lines around them. It's broken up into little sections. Okay, those are each called domains. Now, a domain is an area within an object where your magnetic fields for each one of your electrons actually line up with each other. So they don't cancel each other out, they line up with each other. Now, that's not saying that they're all lined up, it's just saying that in certain little sections of your object, they are lined up. And those little sections are called domains. Okay, now ferromagnetic materials, the reason it's called ferromagnets is because the main one, the one we see most often, is iron. And we know that the chemical symbol for iron is Fe. So that's why we refer to these as ferromagnets. And in ferromagnets, like we've seen here, your domains, you've got separate domains where the electric fields are actually lined up. And then here, this is very important. The cool thing about ferromagnets is if you take a ferromagnet and you put it within the magnetic field of a permanent magnet, which we'll get to, then you can actually turn your ferromagnet into a magnet. Okay, so it will actually act like a magnet, but it will only be temporary. You cannot turn it into a permanent magnet. Okay, so you can take a ferromagnetic material, put it within the magnetic field of a real magnet, a permanent magnet, and it will turn into a temporary magnet. Then after that, we're going to look at permanently magnetic materials. So here again, we've got domains, but here, because our domains are all lined up, so in each domain, the electric field of each electron is lined up, and in addition to that, each of the domains are also lined up, which means overall you have a net magnetic field, and the object is considered to be magnetic. So if we look at this blocky over here, so I've said it's a nickel block, and the direction of most or all of the magnetic fields are pointing in the same direction. So that means they're all or most of them are lined up, which means we end up with a magnetic object. Okay. Now, when you have a magnetic object, it has, depending on the direction of your magnetic field, so you can see here all of our arrows are pointing to the right, eh? So with that magnetic field, it means you've obviously got two distinct ends to your object, and we call those the poles, and you have a north pole and you have a south pole. Okay, now very important, please, your south pole and your north pole are arranged so that the magnetic fields are pointing from your south pole to your north pole. Okay, so they're going from the south to the north. And then also very cool, that means if we were to break our magnet in half or break it in half again, break it into millions of little pieces, doesn't matter how many pieces you make, you will end up with smaller magnets because those domains are still lined up. Okay, you have fewer domains and they're smaller maybe, but they're still lined up. So kind of like an earthworm, you know, that I think it's a myth though, that if you cut an earthworm in half, you get two earthworms. I don't know, but if you cut a magnet in half, you get two magnets. Okay, then attraction and repulsion. I'm sure you've all already seen this in real life. I'm sure you've played with magnets and you've tried to force two ends together and it repels. So that has to do with the poles. Okay, so if you try and force two like poles together, they will repel each other. You'll end up with a repulsive force. And if you try and put two opposite poles together, they will attract each other and stick together. Okay, so two norths together, you'll have a repulsive force. A south next to a north, you'll have an attractive force. And obviously, if you had two souths and tried to push those together, you would also end up with a repulsive force. Okay, now this is something that you will be asked to do definitely in tests or an exam. Okay, they'll give you a magnet and they will ask you to draw the magnetic field lines. Now, when we represent a magnetic field, firstly, what is a magnetic field? So formal definition here in the blocky, you need to know it. It is a region in space where a magnet or object made of magnetic material will experience a non-contact magnetic force. Okay, so very important you have all of that, please. Then, so just a little bit about magnetic fields. All magnetic objects are surrounded by a magnetic field that gets weaker as the distance from the object is increased. Okay, very important. We'll look at this a lot in grade 11 and in grade 12. The fact that as you increase the distance from the magnetic field is weaker. Okay, so that's this here. The magnetic field that gets weaker as the distance from the object is increased. That's got to do with Coulomb's law, which you'll learn next year. Then magnetic fields can be represented using field lines. Okay, they're not real, they aren't lines that exist in real life, but it's just a way for us to represent the field. Now, when we draw these lines to represent the magnetic field, there are these 3 points. These are the 3 rules. Okay, so firstly, the lines start at the North Pole and end at the South Pole. Okay, the lines never cross over each other, and that the closer the lines are together, the stronger the field is at that point. So if we just quickly skip over that and look at this diagram, you can see over here, the lines, if you can see where I'm pointing, the lines are much closer together. That means that the magnetic field there is very strong compared to if we look over here, the lines are a little bit further apart. That means over there, the magnetic field will be a bit weaker. Okay, now when you draw it in a test or an exam, you can draw a 2-dimensional representation like down here, but just so that you know, in real life it's not in 2 dimensions. The magnetic field exists in all 3 dimensions. Okay, so it'll go around the outside of the magnet as well as on top and below the magnet. Okay, now there's 3 scenarios. Either you can have a single bar magnet, or you can have 2 bar magnets where you've got repulsive force, or 2 bar magnets where you've got attractive force. Okay, so if we first look at our single bar magnet, you can see those 3 rules being followed here. Okay, the lines never cross each other. They start at the North Pole and end at the South Pole. You can see that by the arrows drawn. So please make sure when you draw your arrows coming, your field lines coming out of the North Pole, obviously these ones here that sort of just end there, it will make its way, it will make its way all the way around, but it'll keep going. You don't have enough space on your page really, so you're welcome to actually just draw a few just coming out and ending there. Make sure you end it off with an arrow. The ones that go all the way from north to south, put an arrow in the middle to show it's going from north to south, and then the ones that are coming in at the South Pole, draw little arrows coming into the South Pole. Okay, then if we look at repulsive and attractive forces when we've got two bar magnets, so here, looking at the repulsive forces when we've got two norths facing each other, it's basically like drawing a single bar magnet's electric field when you look at the end, the south end here and the south end there. It becomes a little bit different though when you look in the middle where you have your two norths facing each other. So there, those field lines are actually going to push each other away. Okay, because it's repulsive force, the field lines from that magnet coming out of the north will push the field lines from that magnet coming out of the north. Okay, so you're going to end up with a little bit of a skewed diagram. It's going to push them further out, and you'll also notice in the middle here there are no field lines, and that's actually a bit of a dead zone. If you could manage to, in the very center of two north poles, put a magnet there, that magnet will feel absolutely no magnetic field. There is no magnetic field in the very center there. It's a dead zone. Okay. Then if we look at attractive forces, so if I were to take this magnet and flip it around so that I've got the South Pole facing the North Pole of that one, then again very similar, but now instead of these magnetic field lines coming out of that north and going around and coming in its own south, it'll rather go from this north to that one south because it's closer. Okay, and we have attractive forces, and again, make sure that your field lines don't cross. If you're asked to draw this, draw in your arrows, and make sure that you show that the closer you are to the poles, the stronger the force is, and as you get to the center of the magnet and further away from the magnet, those field lines get further apart because the magnetic field is weaker as you get further apart. Okay, now I quickly want to show you a little video on YouTube. I hope it's going to line up properly to show you what this actually looks like in real life, what the magnetic field looks like in real life. So what this man has done is he has taken a bar magnet and put a piece of plastic on top of it, and then he's scattered some iron filings over the top. So iron filings are just sort of very, very, very small flakes of iron, and remember iron is a ferromagnet, which means if it's in the presence of a magnetic field, it will behave like a magnet. Okay. So there's his bar magnet. He's put a piece of plastic over top of it, and now he's scattering his iron filings over it. And you'll see that those iron filings actually arrange themselves sort of like the diagrams that we've seen here. They're arranging themselves so that closer to the poles, they are close together, and as you move towards the middle and further away from the magnet, they become further apart because the magnetic field is weaker. Now he's sort of tilting the camera so you can kind of see that it is in 3 dimensions. Okay, these iron filings at the north and at the south pole are sticking upwards as well. It's pretty cool. It's in 3 dimensions, and you can actually see them arranging themselves like the magnetic field diagrams that we saw. Just pause it there and go back to the Word document. So then so there's magnetic field lines, and then you also need to know a little bit about how this is applied on Earth. Okay, so the Earth's magnetic field, it's pretty cool that Earth has a magnetic field. You can sort of imagine in the very center of the Earth a bar magnet. Okay, with the north up there and the south down there. Now you've all heard of the North Pole and the South Pole in geography before, but the Earth actually has 2 sets of poles. Okay, it's got a magnetic north and a geographic north. Now, so let's just read what we've got. The Earth's magnetic field has been measured very precisely, and scientists have found that the magnetic poles do not correspond exactly to the geographic poles. So our magnetic north pole is approximately 11.5 degrees off compared to our geographic north pole. Okay, now in terms of how a compass works then when we're on Earth, is firstly let's read down here. A compass is an instrument which is used to find the direction of a magnetic field. A compass consists of a small metal needle which is magnetized itself and which is free to turn in any direction. Okay, so the needle of a compass is a magnet, and that magnet can rotate freely. Now, the way that it works is when you place a compass within the magnetic field of an object. Now, usually the magnetic field of Earth is stronger than any other magnetic field that you might have around you. Obviously, you can disrupt a compass by putting a very strong magnet near it. Then it won't tell you where north is according to Earth. But if you use it properly, then the needle will actually line up in the same direction as the Earth's magnetic field. Okay, so your needle will rotate so that it's pointed in the same direction as the magnetic field of the Earth, which is pretty cool, which is how it tells us where north is and where south is. Okay, yeah, I'm not sure how helpful this video was. Please let me know so I can see if I should do one for the theory for electrostatics as well, because I mean you could basically just read these notes. That's what I've done. I've read the notes with you. So let me know if it was helpful so I know if I should do one for electrostatics theory as well. And you're going to answer these questions down below for me. Okay, so these are all past paper type questions. There are actually past paper questions, so you can see it's usually sort of a multiple choice question followed by an extended question where they will most likely ask you quite a bit of theory and then generally also ask you to draw magnetic field of something. Okay. Yeah, that's it. Let me know if you are stuck, if you need any help. If you are, though, the internet is brilliant. You can Google most of the stuff for magnetic fields. It's pretty much just theory. It's only really when it comes to the maths that Googling might not be great because the most resources are American and we do the math slightly differently. Okay, I'm rambling now. Let me know if you get stuck, please. And yeah, stay safe. I'll see you guys soon, hopefully.